So, welcome to lectures on engineering mathematics 2, and this is module number 1, lecture number 2 on vector and scalar fields. So, today we will cover that what are the vector fields and what are these scalar fields, and most importantly we will also cover the concept of this directional derivatives, which is very important, and it is the generalization of the derivative what we have learned in calculus. Okay, so these vector field are these functions basically that map a point to in a space to a vector. So, now instead of a scalar value, we will have the vector value, like in the previous lecture we have learned the vector functions of a single variable. So, here instead of single variable we can have the several variable, but the output will be also a vector. So, we can define such a function by this vector here f, whose components are given by this f, g and h. So, what is important here that we are supplying a point here in a space, and we are also getting as a output a vector. So, this is what we call in vector setting as a vector field. So, these are the functions, for instance, from R3 to R3. The example, the well known example we can think of is the velocity of the air, for instance, inside a room is defined by a vector field. So, because at each point in the room we have a function which can be a velocity function, which is what we call the vector field. So, another example is the gradient, which we have learned in the last lecture. So, the gradient of a function is also an example of the vector field. So, for instance, we have a function here of two variable 3x square y plus 2xy cube, and if we find the gradient, then we have a vector function here which is given by this expression. And then so this is the function which takes a point in R2 plane and gives a vector in R2. So, again we can call this as a vector field in the plane. Now, the question is that how to visualize these vector fields. That is another important component here which we will discuss through this example. So, let us consider that the vector field is given by this yi minus xj by this function. What is important that the magnitude of this function here f at xy is given by the x square plus y square. So, what we can note down here that the vectors of equal magnitude, because the magnitude is x square plus y square. So, the vectors of equal magnitude lie on the circle x square plus y square is equal to c, because the magnitude is c now. So, if we have 1, for example, c is 1, then all the vectors of magnitude 1 will lie exactly on the circle, or we change the c to 2, for instance, then all the vectors of magnitude 2 will lie on the circle x square plus y square is equal to 2. So, through these level curves we can define the vector valued functions. So, in this case we have drawn two cases, like two circles only. So, x square plus y square is equal to 1, the outer one here is x square plus y square is equal to 2, but we can draw many more just changing the value of c. So, for instance, now we want to visualize here that how this f10 at the point 10. So, we have this point here 10, and the value of this vector function is given by the minus j. That means, in this direction here opposite to the direction of j. So, this is the visualization. So, we have a vector here at 10 which is given by this minus j, and so on at each of these points on the circle we will have a vector of the same length 1, because this is the circle here x square plus y square is equal to 1, and the magnitude of this given vector on this circle will be 1. So, at any point if we draw a vector, so that magnitude will be 1. So, for instance, we take another point, the 0 1. So, x is 0 and then y is 1. So, at this point here x is 0 and y is 1. So, it is given by I. So, that means we have this I, so which can be again described by this vector. Similarly, we can talk about the another point -1 and 0. So, here we have the j, the vector is j. So, in this direction, and again 0 -1 we have in this direction. So, that is the visualization on this particular curve we have seen for this vector. So, these all vectors have the length 1, but for instance, if we draw from the outer circle whose radius is 2, now the vector will be just double in length than what we have in this circle 1. Similarly, so we can have several these concentric circles, and on each circle we can draw the direction of these vectors. So, we can visualize that how this vector field looks like in this case. For instance, we have this 2 dimensional setting. So, coming to the scalar field, so these are the functions that map a point in a space to a scalar value. So, a scalar field means we have the value of the function is a scalar, not a vector. So, a vector field over a plane, or it can be a solid region, is a function that assign a scalar to each point in R. So, we will as input, this will be a point in the, it can be in 3 dimensional space, but it will assign a scalar value. So, for instance, this one f x y z given by this one. So, this is a scalar value. So, therefore, we have the we call it a scalar field. For instance, the temperature inside the room is defined by the scalar field, because temperature is a scalar quantity. So, at each point of in the room, we have some function that can tell us the temperature of the room. So, in the context of this vector, simply this a real valued function of several variable is called a scalar field. So, there is nothing new here, only the term the scalar field will be used in this context of vectors. Otherwise, these are the functions of the several variables. So, for example, we have f x y is equal to 2 x square plus y square. So, again here the visualization, either if it is 2 dimensional, we can just directly plot, or there is another way which we can visualize by this level curves in 2 dimensional or level surfaces in the 3 dimensional. So, here we will take like this 2 x square plus y square, putting some constant, and for varying these constant we can have different curves there, and these curves will tell that the value of this function is same on this curve. So, for instance, if we plot this for taking different value of the constant, so if we set to this constant here and varying this value of the constant, we can get these parabolic curves, and on each curve the value is at any point is same. So, that is what the visualization we can think of for such functions. Okay, coming back to this directional derivative, which I mentioned, it is a very important concept which we will study now. So, we are talking about the directional derivative of a scalar field. So, suppose we have f x y z a scalar field, and at a point this x naught y naught z naught along a vector b. So, what is the difference here? What we are calling the directional derivative? We have studied already the derivatives, mainly the partial derivatives in the direction of x, partial derivative with respect to y, partial derivative with respect to z. But if you want if we want to have the derivative of a function in a given direction, not in the standard direction x, y, z, then how to compute that, because that is more general and more interesting, because our interest may be that how this function changes in a particular direction, not just with respect to x, y and z. So, here the concept of this derivative will be generalized by this given direction b. So, our interest is how this vector how this scalar f, this function f changes in the direction of b, meaning, so this is our setting. So, we have a point p, our interest, where we want to get the directional derivative in the direction of this vector b. Suppose the b is a unit vector. So, if we take another point q here on this line, which is passing through this p in the direction of b, then this can be given as p naught plus this t times b. that is another point here, the q or the general point q on the line. So, if we consider this the position vector of this function here on this line C, that will be given by p 0 plus t b, or we can define by general function as we do x t, y t and z t, but we can, since the b is given and the p naught is given, so that r t will be given by p naught plus t b. And the rate of change of this f in the direction of b, we can compute as that f evaluated at q minus, because now we are in the direction of b only, along this line we are moving in the direction of b from the point p. So, what we are computing here, that f at q minus f at p divided by this distance t here, and then we are interested that what will happen to this quotient as t approaches to 0, because we want to find this directional derivative at the point p. So, this is exactly the df over dt we want to compute, and using the chain rule we can have, because f is given by this one, f x y, f is a function of x y z. So, we can have the partial derivative with respect to x and dx over dt, partial derivative with respect to y dy dt and so on. And now, this we can rewrite in the vector setting as this which is the del of, or the gradient of f into this dx dt, dy dt, dz dt, and that is exactly the r prime, the derivative of r. So, what we have here, the del f into dr over dt, but the interesting is here that dr over dt is nothing but, so if we have this r t is equal to p naught plus t b. So, dr over dt is just the vector b. So, this is the vector b, because that is the tangent line at that point. So, we have this dr over dt is just the b. So, the gradient f evaluated at x naught, y naught, z naught multiplied by this b will give us, so b was the unit vector. So, this will give us the change here, the rate of change in the direction of this b. So, at any point the directional derivative of f represents the rate of change in f along b at the point p, and this is denoted by this dbf, or and it can be computed as the gradient of f evaluated at the point p and its dot product with the unit vector b. So, we will go for some examples. So, find the directional derivative of this f x y is equal to 4 minus x square minus 1 by 4 y square at the point 1 2 in the direction of this. So, the direction is given I plus square root 3 j. So, first we need to compute the unit vector in this direction of this u to get this. Also, we need to evaluate the gradient of f, which is thus the partial derivative of this with respect to it, that is minus 2 x ith component, and the yth the second component will be with respect to y, that means you will get here 1 by 2 y. So, that is the gradient f, and we want to evaluate at 1 2. So, this will be given by minus 2 I and minus j. So, this is the gradient of this function f at the point 1 comma 2. The b, which is the unit vector in the direction of this vector u given u I plus square root 3. So, the length of this vector is 2. So, we have divided this by 2, 1 by 2 and square root 3 by 2, that is the unit vector in the direction of u. And now, the gradient, so the directional derivative of this f in the direction of b will be given by this dot product. So, we have the gradient of f at that point, and then we have the unit vector b, and this dot product will give us that directional derivative, which is given by minus 1 minus square root 3 by 2. Another example, so we want to find the directional derivative of this scalar field 2 x plus y plus z square in the direction of I plus j plus k. and we want to evaluate that at origin. So, again a similar example, we have to get the gradient of f, that is 2 I plus j plus 2 z k, and then the directional derivative will be given if we multiply this by the unit vector. So, the unit vector in this direction I plus j plus k will be given by this expression, and if we make this dot product, so we can find out the directional derivative at that point, at the point 1 1 1 in the direction of this I plus j plus k. And if we want to evaluate this at origin, so we can put this z to 0 and the value will be square root 3. Okay. So, now we want to get the maximum rate of change of a scalar function, and where this directional derivative plays an important role. So, the rate of change of f in the direction of a unit vector b is given by this directional derivative, that is precisely the how we define this directional derivative. And if we see that this dot product here is the magnitude of this delta f, magnitude of b and cos theta. So, this magnitude of b is 1 because we take this unit vector there. So, this directional derivative or the rate of change of f in the direction of b is given by del f multiplied by cos theta. Now, it is important to note here that this rate of change in this direction of vector b will be maximum when this cos theta will be 1, that means the theta will be 0. So, the theta is the angle between the del f and the unit vector b. So, if we take the unit vector b in the direction of del f, so if we take if we compute the directional derivative in the direction of this del f, then the magnitude is going to be the largest one, the maximum one. So, this is the point here, that the rate of change is maximum when the theta is 0, that means in the direction of the gradient f. The rate of change is minimum. So, when this is going to be minus 1 for instance. So, the theta, when theta is pi, that means in the opposite direction of delta f. So, the rate of change is minimum when theta is pi, and this is the direction that is opposite to the del f. So, we got two directions. In one direction the rate of change is maximum, that is the direction of the gradient f, and there is another direction where the rate of change is minimum, which is just opposite to the del f. So, again to summarize, that the gradient vector delta f point in the direction in which f increases most rapidly, and the minus del f points in the direction in which f decreases most rapidly. So, this is a very important concept which is very much used in many applications, because by simply computing this delta f, the gradient f, we are getting now the direction where this function, this particular function f changes most rapidly. And on the other hand, we can also get by this minus delta f a direction where the delta f changes, the decreases most rapidly. So, here let us take an example. Here f x y z is equal to x square plus y square minus 2 z, and we want to find the direction of maximum increase of f at this point 2, 1 and minus 1. So, we compute the gradient of f. So, gradient of f will be computed by taking the partial derivative with respect to x. So, that is going to be 2 x, and the second component will be 2 y, the third component will be minus 2. So, the gradient of f will be given by 2 x, 2 y and minus 2. What do we need? We need the direction of maximum increase at this point 2, minus 1 and 1. So, the direction for the maximum increase will be given by exactly the gradient of f, the direction of the gradient of f. So, we will evaluate the gradient of f at this point. That means we have 2 into 2, so that is 4 I, then we have minus 2 j, and then we have here the minus 2k. So, this is the direction of maximum increase of this function. So, if our interest is that in which direction this function increases most rapidly, so that will be the direction given by this gradient of f. So, just a note, this concept of maximum increase or decrease is very useful for optimization problems, which is well understood from this discussion, because we are, by finding this gradient, we are actually getting the direction of maximum increase, or by finding this minus grade f, a direction where the function decreases most rapidly. So, in this way, if we move from a point in the direction of this gradient, we can either go in the direction where the function is increasing most rapidly or decreasing most rapidly if we go in the direction of minus del f. So, in either way, this is useful to find the maximum value of the function or minimum value of the function. So, there is a well known algorithm, so called this gradient ascent or descent approach, which is very popular for finding local maxima and minima. So, we start from a point, compute its gradient and go. So, we start from a point and then let us say we find out the gradient of f, that is we are finding the maximum, for instance. So, we will go in this direction with some step, then again we will find the direction, then again we will find the direction, and finally we will this process will take us where the function has its maximum or the local maximum. And similarly, if we go with the other direction minus del f, then we are able to search for the local minimum of the function. Okay, so these are the references we have used to prepare this lecture. And just to conclude, so we have defined that what are the vector fields. So, these are the function that maps a point to a vector. So, in general we have a function here from R n to the R n. So, the input will be also from the R n and the output will be also in R n, that is what we call the vector field. And the scalar field, these are the functions of several variables which we studied in the calculus. So, these are the functions that map a point to a scalar, and the important concept which we have covered here, that is the directional derivative, which we can compute just by the gradient of f at a point p, and then if you multiply this by the direction where we want the rate of change of this function, and this is the unit vector. So, we will get this directional derivative of the function, which has several applications in optimization, for instance, and other numerical process. So, I thank you for your attention.